In this video, we are going to have definition, theorems and examples in the section 2.5 given in topics in algebra by N.Herstein, namely a counting principle. Now, what is that we are going to count in this and what is the principle behind it? So, for that, first we'll have this definition which states that if H and K are two subgroups of a group G, then the product HK is all those elements of the form HK where H range over capital H and K is from capital K. So this product is defined in this way. Now we know that if H and K are two subgroups of a group G, then H intersection K is a subgroup, but H union K is not a subgroup of G. Now here what we have described is neither H intersection K nor H union K, but the product HK. So we can see from the following illustration that HK is just a subset of G and as such is not a subgroup of G. So for example, you consider G to be S3, which we have been using the set consisting of epsilon, alpha, beta, gamma, delta, theta. And we consider these two subgroups, namely H, which consist of epsilon alpha, and K consisting of epsilon and beta. Now we consider the product HK. When we compute that, we have epsilon with epsilon, so you have epsilon, and alpha with epsilon, so you have alpha, and epsilon with beta, you have beta, and alpha with beta gives you delta. That's from this table that we can see. Alpha with beta gives us delta. So you have this. Now if you compute KH, then we have first we consider this. So epsilon with epsilon, and then beta with epsilon, and similarly, so that gives you epsilon beta, and then epsilon with alpha, that gives you this, and then beta with epsilon. So here beta with beta with alpha, that gives beta with alpha theta. So that is what is written here. So we know pretty well that the subgroups of S3 proper subgroups are the set consisting of epsilon alpha, epsilon beta, and epsilon gamma, and the fourth one is epsilon delta theta. So these are not at all subgroups of S3, they are only subsets. When we consider alpha beta, we are getting of course delta. Alpha beta gives me delta, but when you consider beta delta, it is gamma that is not present. So closure fails. So this cannot be a subgroup. It is only a subset. And the same way, if you consider alpha with beta, that's delta. That is not present here. So HK and KH can only be in general subsets and not a subgroup of the given group G. And from these two, we also notice that HK in general need not be equal to KH. Now, in the following theorem, we are going to have a criterion for HK to be a subgroup of the given group G. So HK, if H and K are subgroups of a group G, then HK is a subgroup of G if and only if HK is equal to KH. Now we'll first assume this. Let HK be equal to KH, and we'll try to prove that HK is a subgroup of G. So to prove that HK is a subgroup of G, we need to prove that HK is closed and every element in HK has its inverse in HK. So first we'll establish this subdivision. Suppose X is HK, two elements that we need, to show that XY is, HK is closed. We'll have to consider two elements X and Y and show that this XY is also present in HK. So we consider X in HK, so you can write your X as HK, and similarly Y in HK, you take it as some H prime, K prime. Now you consider the product, so replace your X by HK and Y by H prime, K prime. Now XY, when we consider, which is given by this, by associativity we can group like this, and this KH, where do we have? this KH prime, where do we have? That is in KH, obviously. But KH is nothing but HK. So how I can write my KH prime? You can write it as KH prime to be some H2 K2. So with the H2 in capital H and K2 in capital K. Now again, by associativity, when we group them, this is what we get. So H2 K2 K prime. Now this is obviously a member of H. H is given to be a subgroup. So for H and H2 in H, the product should be there in H, and K2 K prime are in K. So the product should be there in K. So for XY in X and Y in HK, we have XY also, the product also belonging to HK. So that shows that HK is closed. Next, we will prove that for any X in HK, its inverse is also in HK. So we shall consider X to be in HK. So we can write it in the form small h, small k. So when we consider X inverse, we have HK the whole inverse, which is K inverse, H inverse. So we get this. And obviously it is present in capital KH. Now X inverse belongs to KH, but KH is equal to HK. So X inverse belongs to HK. So for X in HK, we have proved that X inverse also to be in HK, and therefore HK is a subgroup. Now for the converse part, we shall assume HK to be a subgroup of G. What we need to prove is HK is equal to KH. So we prove this by showing that KH is contained in HK and HK is contained in KH. So these two subdivisions, once we establish, then from these two, what is required we'll get. Now to prove the first one, we consider for any H in capital H and K in capital K, H inverse, K inverse. See, this part is to be remembered. How we proceed for this, we start with H in capital H. It's a subgroup, so its inverse will be there in H. Similarly, K is a subgroup. The inverse of this will be there in K. So the product here considered not as HK but as H inverse K inverse. So H inverse K inverse belongs to HK. So when we consider KH, we know that it can be rewritten this way: H inverse K inverse the whole inverse. And this H inverse K inverse the whole inverse belongs to HK because HK is a group. Here we have said that this is in HK. This part is to be again, let me tell, this has to be remembered. Only if you consider in this way, you can talk about KH by considering its inverse. And that will exist in HK because HK is a subgroup. So this K is an arbitrary element in capital K and this H is an arbitrary element in H. So you have your KH to be contained in HK. So that proves the first part. Now for the second one, we'll consider X to be in HK. So then because HK is a subgroup, its inverse is in HK. Now you write your X inverse as an element from capital H and an element from capital K. Like this, you have that to be HK. Now you consider X, which you can rewrite as X inverse the whole inverse. Replace this X inverse by this HK. So you have HK the whole inverse, and that gives you K inverse H inverse. That's a member of obviously KH, the product KH. So here too, we need to remember that X belongs to HK because HK is a subgroup. X inverse belongs to HK. Here we consider in this way, and here if these two are not remembered, establishing this will be a confusing one. So now from 1 and 2, these two we have established. So from 1 and 2, we conclude that HK is equal to KH. So whenever HK is a subgroup, HK must be equal to KH. Now if H and K are subgroups of the given abelian group, suppose I am given an abelian group, say G, then in that case, do we have HK obviously to be a subgroup of G? The answer is yes, because once you have G to be an abelian group, capital H K will be equal to capital KH because all the elements in HK will commute H and K, because in G itself it will commute, so naturally in this also it will commute. So as sets they are equal. You cannot equate an element from this one, that is, you cannot have small h small k to be equal to small k small h. That is not possible. But you will have as sets, the elements in this collection will be equal to the elements in this collection. So the as sets they are equal, not individually. Like when you have, say, the set consisting of 1, 2, 3 is definitely equal to the set consisting of 3, 2, 1. But you cannot equate 1 to 3 and like that. You cannot equate. Elements cannot be equated. As sets they are equal. So you have so we have Hk to be equal to Kh. Therefore, by the above theorem, Hk must be a subgroup of G. Now, the main proof of this section is to prove that if H and K are finite subgroups of a group G, then order of Hk is equal to order of H into order of K divided by order of H intersection K. So this is the main theorem in this section. So this only gives you, this is the principle, that what principle that that is involved in counting the number of elements in this product Hk. So that is what is given as the title of this section, a counting principle. Now before we proceed to prove this, let us have illustrations. So once you understand the illustrations, then the theory behind improving this theorem will be very clear. Now first we will find the number of repetition of elements in Hk. See, given H and K, we know how to find the product Hk. Now when we find the product, there may not be any repetitions or there may be repetitions. So it depends on what H and K that you are considering in the given group G. Now suppose I consider G to be S3, which we are using repeatedly, epsilon, alpha, beta, gamma, delta, theta. And you have your epsilon, alpha, beta, gamma, delta, theta being given by this way. Now in this we shall consider H and K to be epsilon alpha and K to be epsilon delta theta. Then we shall compute what is the product Hk with the help of this table. So when we compute this, see, H, I have considered capital H to be epsilon alpha. So epsilon alpha are the values taken by my H, and epsilon delta theta the values taken by K. So when we consider this product, we get we have to make use of this table to fill up these cells. So epsilon with all these elements, that gives us epsilon delta theta, very obvious. And alpha with epsilon alpha, alpha with delta. When we consider alpha with delta, it is beta, and alpha with theta is gamma. Alpha with theta is gamma. So this is what we have. So the product S3, the product Hk, they consist of elements epsilon, alpha, beta, gamma, delta, theta. So my Hk is exactly equal to my S3. My Hk is exactly equal to S3. And here all the elements are occurring only once. There is no repetition. And not only that, H intersection K gives me just epsilon. So is there any repetition when we find our product Hk? Absolutely no. You don't have any repetition. All are occurring only once. So number of repetitions of elements in Hk, there is no repetition. Actually, there is no repetition. Number of repetitions means it occurs only once. It occurs only once. So order of H intersection K, because H intersection K is singleton E, you have just only one. Only once it comes. We cannot even use the word repetitions, but for the rest of the cases we are using that, so that is the reason here we have mentioned that. Now we shall consider another example. G, the quaternion group, plus or minus 1, plus or minus I, plus or minus J, plus or minus K. We shall take H to be 1 and minus 1, this subgroup, and K to be 4 element subgroup, namely plus or minus 1, plus or minus I. So H consists of only 2 elements, so 1 and minus 1, here we have written, and the elements of K are listed here. Now our job is to find 1 with all that, so we get this, and minus 1 with all this, so we get this. So 1 with 1, we have the same because 1 is the identity element in that group, so you'll get the same. Now coming to this minus 1, you have minus 1 into 1, minus 1, minus 1 into minus 1, plus 1. Minus 1 into I gives you minus I, minus 1 with minus I gives you I. Now we will look at, so these are the elements of HK. These are the elements of HK. H consists of 2 elements, K consists of 4 elements, so 8 elements. Now we'll say, just check whether there are any repetitions or not. 1 is repeated twice. Minus 1 is also repeated twice. I is repeated 2 times. Minus I is also repeated 2 times. So, and when we consider the intersection of H and K, obviously it is plus or minus 1. H intersection K is 1 and minus 1, and number of repetitions. We have seen that each element is repeated twice, and that happens to be order of H intersection K. Now we shall have still one more illustration. Now we will consider S4, the symmetric group of degree 4. These are the 24 elements that we know already. These are the 24 elements, and in this we consider these 2 subgroups. We shall name them as H and K. These are the subgroups that we consider. As before, the elements of H listed here, elements of K listed here. So when we compute the product, this is the product that you get. We know how to multiply 2 permutations. So when we do, for example, we'll have 1. This one we shall consider. See here, 1 is taken to 2, 2 is taken to 1. So that means 1 is taken to 1. So that is not written here. Then 2 is taken to 3, and here 3 is taken to itself. So 2 is taken to 3. Then 3 is taken to 1, and here 1 is taken to 2. So 3 is taken to 2. So we can compute the product HK in this way to fill up this table. Now having got this, we will see that how many times an element is repeated. If we consider epsilon, it occurs here once, twice, 3 times. And 1, 2, once, twice, thrice. Similarly 2, 3. Here 1, 2, 3. And 1, 2, 3. Here 1, 2 and 3. 1, 3, 2, here, here and here. So all the elements are repeated 3 times. So totally how many? See here we are getting 3 times 6, so 18 elements. But each one is repeated 3 times. So that means we have to consider when we count the number of elements, repeated elements, we need to, we should not consider. So that means totally we have only 6 elements, but each one is repeated 3 times. So the cell gives us 18 elements. And here we can easily see that the order of H intersection K is just our H itself. Epsilon 1, 2, 3, 1, 3, 2. And number of repetitions of elements in HK is 3. Each one is repeated 3 times. So that is order of H intersection K. So how many times that is repeated, that is the number with which we have to divide the total number of elements in the product. So that is the usual procedure. So having got from these illustrations that idea that order of H intersection K times elements are repeated if at all there is any repetition. So with this idea in our mind, we shall proceed to prove that theorem If H and K are finite subgroups of G of orders order of H and order of K respectively, then order of HK is order of H into order of K divided by order of H intersection K. Now, first we shall consider H and K be finite subgroups of G of order of H and order of K respectively. Now, in the proof of this theorem, we are going to have two cases. One is H intersection K is just singleton E and H intersection K is not equal to singleton E. That is, it has more than one element. We had in the first one, in the first illustration, H intersection K consisting of only singleton E. So, in this case, we will prove that there is no repetition. Okay, number of repetition, one we said, that is nil repetition, which is same as saying nil repetition. Each element occurs only once. And in the second case, depending on how many times, what is the order, so many times the element is repeated. So the same thing theoretically that we are going to conclude. So for that only we are discussing these two cases. H intersection K is singleton E and H intersection K is different from the identity element. First case, H intersection K is just singleton E. We are going to claim that there is no repetition in HK. Suppose not. That is, suppose there is a repetition. That is, HK is again occurring as H1K1, or say H1K1 is same as HK, either way, with H not equal to H1 and K not equal to K1. We shall name this as statement P. Now, we'll pre-multiply both sides by H1 inverse and post-multiply both sides by K inverse. Then we get this. So, in this H and H1 inverse are present in H, and here K1 and K inverse are present in K. So, this as such is in H, but being equal to this is therefore present in K. And in the same way, this one as such is present in K, being equal to this must be present in H. So, that is why we say that these two, when we consider, they are in H intersection K. But we have assumed H intersection K to be singleton E. So, this element can only be E, and in the same way, this element can only be E. So, identity element. So, you have from that H equal to H1, and from here K equals K1. But here we have mentioned in statement P that they are different. So, that's a contradiction to statement P, and therefore, there is no repetition in HK. There is no repetition in HK. Now, case 2 we will have. So, when there is no repetition, what will happen? Order of H intersection K being equal to 1, we will have order of HK to be equal to order of H into order of K. So, that is obvious. So, now we will go to case 2. H intersection K is not equal to singleton E. So, we claim that there is a repetition in HK, and the number of repetitions is order of H intersection K. Now, since H1 belongs to, if we consider an element H1 which is present in H intersection K, of course different from E. This H1, that's again written, actually H intersection K is not equal to singleton E, and therefore you consider only H1 and H intersection K. That is how it should have been. Now you consider HK. This element, to this element we are going to introduce E, and that E is rewritten as H1 inverse. So this is K actually, this is not K1, this is K. Now this H1 is a member of capital H, and this is H1 inverse. Remember, H1 belongs to K also. So now that this is treated as element of capital K. This is K actually, not K1. This must be K and not K1. So we have these two to be present, these two, and the product present in H, and this one to be present in K. So because H is in H, H1 is in H intersection K, which is contained in H, this step comes, and for this we have this. So this K should be here, not K1. H1 inverse belongs to H intersection K, and that is contained in K. So K is also in K, and therefore this one is in H, this one is in K. Right. So my HK is this. Thus, HK is duplicated in the product at least order of H intersection K times. Now, why do we say this? Because we are able to associate. See, if we have just considered, see, when we write this, introduce E in between H and K, you can also write that as some other H1, not just only in H, and you say that yes, I can write like this. But in that case, because you cannot come to a conclusion that this is an element in H and an element in K, we cannot conclude that. So that means you need to proceed with an element common to both H and K, not just H alone or not just with K alone. So whenever I am writing my HK, I am able to associate that element which is introduced here with H intersection K. So how many times that we can expect the duplication in the product? At least order of H intersection K times. Alright, now we will have to confirm this. That is, we have said that it is only at least. Now exactly order of H intersection K times only it will be repeated. So for that, also since there is a repetition, Hk equals H1 K1. So again, pre-multiplying by H1 inverse, post-multiplying by K inverse, this is what we get. Name that as T. Definitely this is in H, this is in K, so my T will be there in H intersection K. So again the same thing, Hk is which is H1 K1, you are able to introduce this T inverse. Again this is in H, this is in K. So we have the repeated element occurring exactly order of H intersection K times. So you cannot go beyond that. You cannot ask how many ever elements that you have in the intersection. So many ways only you can write your HK like this, not more than that. So the repeated element occurs exactly order of H intersection K times. Now, so you have HK appearing in the list HK exactly order of H intersection K times. Hence, the number of distinct elements in HK is nothing but the total number in the listing of HK, which is order of H into order of K, divided by the number of times a given element appears, namely order of H intersection K. So order of HK is nothing but order of H into order of K divided by order of H intersection K. So how many times that it is repeated, that we know with the illustration, but in this, by associating, whenever there is a repetition, by associating that element with an element in H intersection K, we are able to have that repetition occurs order of H intersection K times. So how many times that it is occurring, we have to divide that number. So we have to divide the product by that number. We have to divide this product order of H into order of K by that product. Now we have a corollary to this. If H and K are subgroups of G, then and order of H is greater than square root of order of G, order of K is greater than square root of order of G, then H intersection K consists of more than one element, that is identity element. Apart from that, you have some more elements. Now let H and K be subgroups of G, then HK is a subset of G, and so you have order of HK to be less than or equal to order of G. So you consider order of G, same thing is again written, but in this way order of G is greater than or equal to order of HK. But you know by the above theorem, this is order of H, order of K by order of H intersection K, and that is replaced by square root of order of G, square root of order of G, and this is retained as such, and this gives us order of G. So being positive, we can cancel them out. So that gives order of H intersection K is strictly greater than 1. Even though here greater than or equal to comes, here strict inequality comes. So you have order of H intersection K to be strictly greater than 1. So H being a subgroup, it will have identity. K being a subgroup, it will have identity. So H intersection K definitely will have identity element. But order being greater than 1, so apart from identity element, it will have some more elements. So that is what this corollary says. So the main part of this section is only this counting principle. How many elements are there in HK is counted, and for that we have this corollary that H intersection K will have whenever we have this to be true. Whenever we have this to be true, then in that case you have H intersection K consisting of more than one element. So that is the these are the definitions, theorems and illustrations that we have in section 2.5 accounting principle. Thank you.